In the previous videos, we've been working some practice problems that all have had something in common. All of the forces in those practice problems have been acting in a single dimension at a time, either y-dimension forces like gravity or normal force usually, or horizontal forces, x-dimension forces. Usually those have been things like friction or a pull or a push force that's horizontal. Now, not to say that those forces will always act in the dimensions that I just assigned to them, but that's been our experience with problems so far. We've had forces that were acting in a single dimension at a time. Now, that's not to say that those problems were one-dimensional. Those problems had an x dimension and a y dimension and forces assigned to each of those dimensions, but all of the individual forces that we added together to find the sum of the forces, those forces were all either vertical or horizontal. In this lesson, we're going to learn how to deal with forces that are diagonal, as we learn about forces that are in two dimensions in the xy plane. And I'm not talking about just using the xy plane to solve force problems. We've been doing that all along. I'm talking about our individual forces that we add together to make the sum of the forces. Those individual forces are going to be in two dimensions at a time. They're going to be pointing diagonally. And we're going to learn how to solve problems with diagonal forces. It's important to note that we've worked problems where all of the forces were in the same dimension. These are the simplest kind of problems. So, for example, our race car problem where a driver was working on his car's suspension and the springs were pushing upward and gravity was pulling downward. Those are both vertical forces. The car was not being pushed or pulled in the horizontal dimension, so there were no horizontal forces at all. Another class of problems like this was the problems where we had somebody riding in an elevator and there was a normal force pushing upward and gravity pushing downward, and there were no side-to-side forces. So these are true one-dimensional force problems. And when I add these vectors together, I get a pretty simple vector sum problem where I'm going to have a net force pointing in the same dimension as my other two forces. And then I can solve for the size of that net force, the acceleration, maybe some value related to the forces. But I'm solving for something in a one-dimensional way in these kinds of problems. We've also worked problems that have a set of vertical forces and a set of horizontal forces. And the vertical forces are all pointing in one vertical dimension. The horizontal forces are pointing in a horizontal dimension. There may be problems like this, where we have this car skidding to a stop. Its tires are locked against the ground, so the force of friction is acting horizontally. And then we have the vertical forces of the normal force from the surface below and gravity pulling downward. Notice that we have our forces organized into two dimensions. We have our vertical forces that are all pointing entirely vertically and our horizontal force. Another characteristic of these problems is that the forces in one dimension cancel because acceleration is in the other dimension. So in this case, acceleration was in the horizontal dimension. That means that the vertical forces must cancel. And putting that all together, I get this vector sum problem that's a little bit more complicated than the one-dimensional problem, but really it's still fairly straightforward. I have my vertical forces being added together and canceling. I'm always adding the way I always add vectors. I start at a specific point. I draw my next vector starting at the head of the previous vector. And then I have to draw the resultant vector from the tail of the first to the head of the last. Where's the resultant going to go? Well, it's going to start at the point where I started and go to the head of the final vector. Notice that my net force is pointing in the same direction as the friction force. It actually, in this case, was the friction force. But even if there was another forward vector horizontally to add to this, the net force would still be in that horizontal dimension. That means that my acceleration is going to be in that horizontal dimension. These problems were all very easy to work one dimension at a time. We can think back to the problem where I had a car crashing into a wall. This is another similar type of problem where I have sets of vertical and horizontal forces. The difference here is that I don't have any friction force in this problem because the force that's being applied horizontally is the normal force of a wall crushing and pushing backwards on the car. So if I consider this problem's vector sum, I have my normal force, my gravitation force, and then the normal force of the wall. So I have a normal force from the floor pushing upward being canceled out by gravity. The normal force of the wall is applying a huge force backwards, accelerating this car to a rapid stop. And then my net force is going to be pointing in the direction of the force from the wall. Once again, my net force is in the horizontal dimension because my vertical force is canceled. These are the types of problems we've been working so far. What's different about forces in 2 dimensions in the xy plane? Well, these are problems that have diagonal forces, forces that are pointing in both the x and y dimensions at the same time. And what we must do with these problems is convert them to the same types of problems we've been working so far. These vector sums are so easy to work with that we're just going to continue to work with vector sums that look like this. And anytime we have a diagonal force in a problem, we're going to convert that diagonal force into its components, the x component and the y component. And we're going to plot those components along the axes where they belong so that we can add those forces the same way that we've been adding forces all along. So let's take a look at an example of a problem that we might work. Here I have that car that just crashed being towed by a tow truck. And notice that the tow truck's cable is pointing at an angle and then going down underneath the car. That's done so that that tow truck has maximum flexibility with how it uses that cable. And let's take a look at the forces that are actually acting on this car. Well, of course, we have the gravity force because this car exists in Earth's gravitational field, so the Earth is pulling its mass downward. There's also going to be a normal force upward from the road. Now, I'm just going to say this car is going to be being towed in this diagram at a constant speed. So the diagram that I'm showing you is for a car towed at a constant speed, but you may be wondering, hey, wait a second, that normal force looks like it's smaller than the gravitation force. So there must be something else that's missing that's going to balance out that gravitation force. Well, is there another force acting on this car? There's going to be some horizontal forces as well, right? There's going to be a friction force resisting the motion of the car as we tow it forward. Now notice I've titled this the force of friction with an R. That R stands for rolling friction because this car is probably still going to be rolling. Normally we would expect rolling friction to be a very, very small amount. We've talked about rolling friction in the past. Rolling friction is just the resistance to an object rolling because the axles are rubbing against something. So no object is going to roll frictionlessly, but usually rolling friction is very, very, very small. However, because this car was just in an accident, it might be that the axles were damaged and things aren't rolling exactly correctly. So maybe the rolling friction is going to be a little bit bigger for this car. But that doesn't solve our gravitation problem because we still have unbalanced normal force and gravitation force. It looks like the normal force is too small here. Well, are there any other forces acting on this car? It's being towed by a tow truck. What's the effect of that going to be? Well, remember, this tow truck is towing with a cable, and cables apply tension forces, tension being a force that just transmits a force from one place to another. So it's transmitting the force from the tow truck. It's probably actually a normal force being applied to the cable as the cable is tightly wrapped around that axle on the tow truck. And it's transferring that force to the car. And tension forces are only ever able to apply forces in the direction of the cable. So because the cable is pointing up into an angle, we need to include that tension force in our diagram at that same angle. So this is the tension force that's acting on the car. And if I were to do a vector sum of these forces, I would find that these forces add up to zero, a zero net force. So that's why this is being towed at a constant speed, because all the forces are canceling each other out. The net force is zero. There is going to be no acceleration. But my question from before still remains. What in the world is canceling out the force of gravity? Shouldn't this be accelerating in the vertical dimension because normal force isn't long enough to completely cancel out the force of gravity? Well, maybe I can get a better view of this if I do what I mentioned in the instructions and I convert my diagonal force into its components. To do that, I'm simply going to redraw my diagonal force somewhere, and I'm going to draw what must be the horizontal and the vertical components of that force to make a right triangle. Now, in my diagram, I can actually replace that diagonal force with its components. There's the vertical component and the horizontal component. That horizontal component must be large enough to overcome rolling friction, exactly because it's not accelerating horizontally, and the vertical component must add together with the normal force to completely cancel out gravity. Let's see what this looks like when I draw a vector addition problem using these new component forces. So here's my vertical dimension, and I continued adding my vectors also in the horizontal dimension. So this is one big vector addition problem. Notice that I've drawn all of my vectors here, and I drew them starting each new vector at the head of the previous vector. And I would draw my resultant from the tail of the first to the head of the last, but the last vector actually went back to the origin, so there is no resultant vector. The resultant sum of these vectors is 0, which is, again, what we would expect. This is the much more useful way to add vectors in two-dimensional problems. I don't want to include diagonal vectors in my vector sums because diagonal vectors are very difficult to work with in their diagonal form. What I'm going to do instead is break all of my diagonal vectors apart into vertical and horizontal components, and then I'm just going to replace them because remember, when I draw the components of a vector, it equals the original vector. It's like adding two numbers together to equal a new number. I can use those two numbers, or I can use the composite added number, and either of them are representations of the same thing. So I'm just going to replace my diagonal vectors with components in all of my vector drawings. Let's take a look at how this works in the context of a real problem. In this problem, we're going to have a tow truck using a cable to tow a crashed 1,080 kilogram vehicle. The truck driver attaches a cable to the rear of the car in a safe place. It's important to do that, making an angle 35 degrees above the horizontal. The cable has a tension of 3,100 newtons, and the car accelerates at a rate of 0.75 meters per second squared. What is the effective coefficient of friction for the force resisting the motion of the car? Now, keep in mind, this car is probably still going to be rolling, but it's not going to be rolling really efficiently because it was just in a car accident. So I don't know what the coefficient of friction is going to be. It's going to be greater than 0 because the coefficient of friction is always a number greater than 0. It's not going to be tiny. It's probably going to be somewhere between 0 and 1. If the car is really damaged and difficult to roll, it's going to be closer to 1. And if the car is still rolling fairly well, it's going to be very close to 0. I'm guessing it's going to be somewhere in between there for this problem for a car that was in an accident. Now let's just take a look at a car being towed using a cable. This isn't the car in our problem, but this is an example of a video of a cable towing a car, and you can see the tension force at work. So here we have a car trapped in the snow. The tow truck is going to start going. You see that there's this chain attached to the car pulling upward at an angle. This is a little different because this car is in a ditch. The car in our problem is just on flat ground. The tow truck is going to gently tow the car forward, accelerating it from rest at a very slow rate. Notice that the car comes back to rest before it actually starts making it up the bank there. And as the car is towed, the wheels begin to roll, and eventually we have towed our car out of the snowy ditch back onto the road. Notice again that the entire time this chain is keeping tension, and the force being applied by the tow truck is being transmitted to the car through this chain at an angle. All right, let's now consider this problem in the form of a vector diagram. This vector diagram looks similar to the previous one, except there's one important difference because this problem describes the motion of this car a little bit differently than I described the motion of the previous car. Can you pick up what the difference is? Now look at these forces that are acting on the car. There's gravitation because the car exists in Earth's gravitational field. There's a normal force of the road pushing upward on the car. That normal force is not as great as it would be if the car was just resting on the ground because we have a tow truck that's towing it at an angle with a chain that's at an angle. So that tension force in the chain is going to have an effect of lifting the car a little bit. Now, its gravitation is going to stay the same because the Earth's gravitational field is going to have the same effect regardless. But the normal force of the road is not as great because it doesn't have to push as hard to overcome the weight of the car. The tension in the chain is doing some of the work. And then We also have a force of rolling friction resisting the forward motion of the car. We need to figure out what the coefficient of friction is. So we need to work with that rolling friction force to figure out what our coefficient of friction is. These are the forces that are acting on one another. If I were to add those together, here is my vector addition problem. And do you recognize what the difference here is compared to our previous problem? Notice that these do not come back to the origin, so there must be a net force forward. My net force is going to be in the horizontal dimension, and that means that the car is going to be accelerating horizontally in the same direction as the truck that's pulling it. But how does that work when I have a tension force that's pulling at an angle? Well, I'm going to take that tension force, I'm going to break it apart into components. I'm just going to note that this is a right triangle with a 35-degree angle. And now that I have my x and y components, I'm going to replace my diagonal tension force with those components in my free body diagram. I don't want diagonal forces in my free body diagram. I want the component forces in there instead. And instead of drawing my vector addition problem this way, I'm going to now draw it out with the component vectors in it. I'm also going to sort my vectors into vertical and horizontal as I add them together. So again, this is a valid vector addition problem. I've drawn each new vector, starting it at the head of the previous vector. I notice that my vertical dimension vectors, when I add them this way, cancel out, and my horizontal dimension vectors do not cancel out, but I'm left with this net forward force. Notice that either way of drawing this vector addition problem, I end with the same forward net force. Now, even though these two vector addition problems are actually equivalent to one another, the one on the right is the one I'm going to use because all of my forces are organized into the vertical and horizontal dimensions, and I can actually use this one to help me solve problems. The other vector addition problem is not useful for solving problems because I won't be able to resolve what's in the x and y dimensions from a diagonal vector. I need to replace it with its components to be able to solve the problem. There are a couple of ways that you can move forward from here solving this problem. Normally I would draw out the two net force equations and then do my substitution and work from there. But I'm just going to take a moment to emphasize something important about these little right triangle diagrams that we use to find our vector components. So you see in the upper right I have my tension diagram, and I have the x component of tension, the y component of tension. In order for me to be able to solve for the sides of that right triangle, I'm going to have to know either two sides of the right triangle, the lengths of two sides, or the angle inside and one of the sides of the right triangle. In this case, I'm given the information that the cable has a tension of 3,100 newtons. And I'm going to assume from the way it's worded in the problem, that's not a component vector, that's the actual diagonal vector, 3,100 newtons. And it's at 35 degrees above the horizontal. With this information, I now know enough to solve for the other two sides using trigonometry. But in order for me to solve for all of the sides of the right triangle, I either have to be given the angle and one side of the right triangle, or I have to be able to find the angle and one of the sides of the right triangle, or be able to find two sides of the right triangle to solve the problem. Let's go ahead and use our trigonometry skills to figure out what the other two sides are here. I know that the x component of this vector can be solved using the cosine function by multiplying the cosine of 35 degrees times the hypotenuse. That gives me an x component of 2,539 newtons. Then I'll use the sine function in the same way to solve for the y component, 1,778 newtons. And I did that by knowing one side, the angle of my right triangle, and then using trig functions to find the other two sides. Those will be very helpful later. Now I'm going to go ahead and solve my net force equations. So first of all, I know that the net force, or the sum of the external forces, same thing, is the sum of all of the individual forces. And this is a doozy. I have 5 different forces that are being added up to make my net force. The normal force, the y component of the tension, the gravitation, the x component of the tension, and the force of rolling friction. Now notice that I've ordered these in sort of an odd way. Like, why didn't I put the two tension forces together? Well, I like to organize these variables in the problem. Remember, addition is commutative, so I can put these in any order that I want. Even vector addition is commutative, so I don't have to put these in a specific order. I'm going to just put my vertical forces together and then my horizontal forces together. So the first 3 I list are vertical forces. The last 2 are horizontal forces. The sum of the external forces is also going to equal either ma or 0 if the acceleration is 0, But I do have acceleration in this case, so I need to include it here as ma. And normally for the next step, you could use substitution and combine these two together. I could certainly proceed in that direction, but I think it's going to be helpful for me to take a moment to take stock of my dynamics variables right now. So I'm going to list my dynamics values in this table. Do I know the mass? Yes, it's given in the problem, 1,080 kilograms. Do I know the acceleration? 0.75 meters per second squared, given in the problem. The rolling friction force I do not know, and the final thing that I'm looking for, the coefficient of friction, is the thing that I really don't know that I need to find. So I'm going to put a question mark there, noting right now that that's what I'm solving for, is the coefficient of rolling friction. I'm probably not going to be able to get to that right away. I'm going to need to find a lot of these other values first. Do I know the x component of the tension force? So I saw for that up above, it's 2,539 newtons. There's no other constants associated with tension force. Tension force has to be calculated in context each time you calculate it in each individual problem. Gravitation, weight. I know a constant associated with weight is 9.80 newtons per kilogram. I know the mass of the car is 1,080 kilograms, so I can find out how many newtons of weight this car has by simply multiplying those numbers together. I get 10,584 newtons. I'm also going to note that the weight force is pointed downward, so I'm just going to immediately note it as a negative value as I add it to my dynamics table. That's the way I do things. I generally decide whether a value is positive or negative as I keep track of it in my dynamics table. So because the x component of the tension force is forward to the right, it's positive, and because gravity is downward, it's negative. What about the normal force? Well, I don't know what the normal force is. Sometimes the normal force is the opposite of the gravity force, but here I'm just going to note that I have this y component of the tension force also pulling up. So I'm going to call my normal force a question mark right now, and there are no other constants associated with calculating normal force. Again, that's one that has to be found out in the context of each problem. And the y component of my tension, I solve for 1,778 newtons up above. Again, no constants associated with tension. Okay, moving on. The next thing I'm going to do on the left is I'm going to note that normal force, the y component of the tension, and gravitation are all vertical forces. And in this problem, my vertical forces all cancel. That doesn't mean they're unimportant. In a problem that involves friction, I'm probably going to need to figure out what the normal force is, and I can only do that in the context of my vertical forces. So I'm probably going to use them later, but I'm going to cross them off in this particular equation because they're not important for the acceleration in the x dimension because they all cancel each other out. What's going to govern the acceleration, the x dimension, is the x component of the tension and the friction force. X component of tension pulling forward. Hopefully it's pulling forward harder than the friction force. The friction force is going to be resisting that forward motion, leading to an acceleration forward of the vehicle as I tow it. Okay, next I'm going to combine my two net force equations, those sum of the external forces. And notice I'm going to use my x dimension forces exclusively because my y dimension forces cancel. So that's why I crossed those off for now. I'm not going to account for them in my forces that are actually contributing to the horizontal acceleration of the car. I'm only going to use my horizontal forces for that. So my x component of the tension force, which I know, plus the friction force, which I don't know yet, is going to equal mass times acceleration. And interestingly, I know mass and acceleration. The only thing I don't know is friction force. Do I have a way of finding the friction force? Well, I know I have this equation, which relates the friction force to the coefficient of friction and the normal force. So this is the force of friction equals mu Fn. Also, I'm just going to note that I'm using the absolute value notation because I'm going to calculate the positive value associated either with friction or with the coefficient of friction. The coefficient of friction is always reported as a positive value. Friction force is going to be positive or negative, but I want to choose that in the context of this problem. So I'm just going to calculate a positive value. Then when I record it in my table, I can choose whether to make it positive or negative. And then when I combine these two equations together, I'm going to combine the left and the right equation here. I'm going to keep the absolute value notation, just noting that whatever I get as a value, eventually here I'm solving for coefficient of friction, I'm going to need to make it positive if it's negative. Now, do you have to be fancy and keep absolute value notation in your equations as you do work on paper? You do not. This is just my way of reminding myself to make any negative values positive, but you can just remember to do that. It's going to be very often that you'll plug in values to calculate a negative value for coefficient of friction, and you just need to make it positive because it's always reported as a positive value. Same thing with friction. You may record a positive or negative value for friction, but you actually need to look in your free body diagram and make a decision whether friction is positive or negative, depending on which way you assign as the positive direction in that dimension. All right, now I'm going to take a break from solving this particular equation for now because I don't have everything I need to know. I'm missing the normal force that I need to solve for the coefficient of friction. So I have two unknowns in this equation. I need to make one of those unknown so that I can move forward. And the thing I can find out is the normal force. Remember how I told you not to completely discount those forces we crossed off before? We crossed them off because they cancel out in the y dimension. We can actually use that to our advantage to solve for one of those values. I can write the equation that the normal force plus the y component of the tension plus gravitation equals 0 because those forces balance each other, they cancel each other out. And then I can note that I know the y component of the tension and I know gravity. So I'm going to rearrange my equation. I like to rearrange my equation so that my unknown variable that I'm looking for is on a side by itself. And then on the other side of the equal sign, I'm going to have negative y component of tension minus the force of gravity. Next, I'm going to plug in the values that I know, being very careful to watch the positive and negative signs. So I know that my ty value is positive, but it's going to become a negative value because it's negative ty. Gravity is a negative value that's going to become positive because it's minus the force of gravity. So when I add these two together, I find that my normal force is a positive 8,806 newtons. Now I also noticed that in my diagram, I drew my normal force way too small. If you look at my free body diagram, it looks like the normal force is about the same size as the y component of the tension force. But the y component of the tension force, as I add this to my table right by it, I notice that that y component of the tension force is only 1,778 newtons. My normal force is much larger. That happens all the time with free body diagrams. Free body diagrams are basically just sketches of what the problem might look like, but as you actually work the problem, you might find that some of your vector lengths are off by a bit. As long as it's not a vector that was completely pointing the wrong direction, you can just continue to work with this free body diagram. It's not really going to change anything. Okay, so now I have my normal force. I'm going to go back to that equation I wrote before, and I'm going to rearrange that equation to solve for the thing that I'm looking for there, which is coefficient of friction. So I'm going to get coefficient of friction on a side by itself. I'm going to put everything on the other side in absolute value brackets because I know that whatever I get, positive or negative, I'm going to make it positive. And then I'm going to plug in the values that I know. And I should know all of these values at this point. Mass is 1,080 kilograms, acceleration 0.75 meters per second squared. I calculated the x component of the tension force to be 2,539 newtons. I'm going to be true to my signs there because it's minus the x component of the tension. So I'm just going to plug in the positive value after the minus sign. And then on the bottom of the fraction, the normal force is 8,806 newtons. I'm going to go through with this calculation. I'm just going to note on the top there, by the way, that 1,080 kilograms times 0.75, that's 3/4 of that. That's going to be a value less than 1,000, and I'm subtracting a value greater than 2,000, which means I am going to end up with a negative value. So I am going to have to switch the sign to make this appropriate for coefficient of friction. But the coefficient of rolling friction ends up being 0.20. Now let's just think, is that realistic for this problem? Rolling friction is usually very, very small, 0.005, 0.001. It's a very, very small value. But again, I have a car that crashed and the tires might be flat. I might be towing it through like dirt and the tires are kind of sliding against the dirt instead of rolling perfectly. My axles might have become messed up so that there's things rubbing that shouldn't normally be rubbing. it's not unrealistic that my coefficient of friction is going to be greater than I would expect for a normal rolling coefficient of friction. So 0.2 is a reasonable response for this problem. All right, and now that we've solved this problem, let's move on to another one. And this one involves a restaurant in an alleyway. The entrance to the restaurant several feet from the sidewalk, so the owner wants to hang a 10-kilogram sign to notify passersby where his restaurant is. The only way to hang the sign is to position one wire horizontally to the right of the sign and the wire on the left of the sign at a 45-degree angle above the horizontal, each anchored into a building on either side of the alley. And that makes sense because there may not be a place to anchor the wires into the building directly where the owner wants, so he has to put one above the other and have this strange configuration of wire and sign. If the wire itself without the sign is just barely slack between the two anchors, so we're not actually pulling them tight, so it's like pulling the buildings toward each other, the extra tension does not yank the anchors from the building. Find the tension in the wire on each side of the sign. So the tension of the wire, by the way, is going to apply a force to each of the anchors. We're not really interested in that in this problem, but we don't want a lot of extra force. You could tie the wire so tight that it is actually pulling on either side, even when it's not supporting a sign. But we're not going to do that. It's slack. The only thing applying a force really is the weight of the sign, and then the tension of the wires is reacting to the weight of the sign. So let's see a drawing of what this looks like. Here's a diagram. My 10-kilogram sign anchored into two different buildings through the wires that are holding it up. One is horizontal, the other is at an angle 45 degrees above the horizontal. And if I were to draw a free body diagram to represent this, I would have to put all of these forces in there. I'd have the weight of the sign pulling downward, a one wire's tension pulling upward and to the left, the other wire pulling to the right. There's no other forces acting on this sign. I wouldn't have a normal force because there's no surface pushing on this sign. I wouldn't have any push or pull forces other than the ones that are being transmitted through the wires as tension. So these are the only forces that could possibly be acting, the non-contact force of gravity and the contact force from the only two things that are contacting the sign, each of the wires. All right. The next thing I'm going to do is draw out a vector addition problem, but this isn't a very useful vector addition problem. It does demonstrate that the sign is not accelerating in any direction, so all of the forces must be canceling one another out. But I can't really use this vector addition problem to help me solve because I haven't broken my diagonal vector into x and y components. So let's do that next. Here I have my vector sum. Showing my components. So I've broken down the tension in wire A into the X component and the Y component being added together. And I can find the lengths of those components if I know one side and the angle or two sides. But I don't know any of the sides from the information that I'm given. So I can't actually use this vector addition problem yet to find the components unless I can figure out what one of the sides of this triangle are. And it can be any of the sides, the hypotenuse or either of the legs, but I do need to know what one of the sides are. I wonder if I can figure that out indirectly another way. I'm not given it in the problem. I am just going to note for now, though, that I do have these two component vectors. I'm going to put those into my free body diagram, and I'm going to draw a separate vector addition problem that shows what's happening. Because those component vectors in my diagram and my addition problem are much more useful for actually solving the problem. I'm just going to note that in the y dimension, my forces cancel, and in the x dimension, my forces cancel, and I have accounted for all of my forces in the diagram and in the vector addition. Okay, the next thing we're going to do is set up our net force equations. My net force is going to equal to the sum of all of the forces, and in this case, I know that this sign is being hung stationary. That's the purpose of a sign, to stay there. So I'm going to note that MA is 0 in this case. The acceleration is 0. The net force is 0. So when I look at these two equations put together, I know that the sum of all of the vectors is 0. Let's take account at this point of the dynamics values that I know, and I could do this in any order. Like I could have had this dynamics table up and have been keeping track of things as I go, but I'm just going to take stock at this point of what I know. The mass is 10 kilograms. Acceleration is 0 meters per second squared. It's not accelerating, not moving at all. The force of gravity, well, I know that the G value is 9.8 newtons per kilogram, the Earth's gravitational field. And that's being applied to a 10 kilogram sign. So when I multiply those together, I get a gravitation force of 98 newtons. That's directed downward, so I'm going to make it negative. The tension in any of the wires is an unknown at this point. I don't know the tension in wire A in either direction, the Y component or the X component, and I don't know the tension in wire B, so that's going to be an unknown as well. There are no constants that can help me to solve for tension forces, so I just have to note that they are unknown at this point and see if I can reason to what they are. Okay, so I do know the weight of this sign, though, and if I look at my free body diagram and my vector addition, it helps me to realize that I do know something else about this problem. I know that in the y dimension, the y component of the tension plus the gravitation is 0. If I rearrange it to just solve for the y component of my tension for wire A, I find that it's equal to the opposite of gravitation. And gravitation is negative 98 newtons. The opposite of negative 98 newtons is just positive 98 newtons. So the y component of the tension force has to be 98 newtons. And that makes sense. The only thing that has an upward force at all in this problem is the wire pointing diagonally. So it's the only thing that could possibly support the weight of the sign. And its upward component force has to be strong enough to exactly support the weight of the sign so the sign's not accelerating up or down. So I can now plug into my table that I know the y component of my tension in wire A. I'm also going to put that in my diagram on the left. But now this is a special type of problem. This isn't going to happen in every problem, but this is a special type of problem because I have a 45-45-90 triangle. And I know that a 45-45-90 triangle is an isosceles right triangle. That means that the two legs are going to be the same length. So if my leg that I have, my vertical leg is 98 newtons, my horizontal leg must also be 98 newtons. And I can go ahead and plug that in here. Normally, I would need to use trig functions with the angle and the one known side, because I knew a side was 98 newtons, so I could use trig functions. If I did use a trig function here, I would find that the other side is also 98 newtons. I would use the tangent function, and the tangent of 45 degrees is 1. So now I can plug that 98 newtons into my table as another thing that I know. As I plug it into my table, I'm going to note that it's pointing to the left, so it has to get entered into my table as a negative value. Things to the right are positive, things to the left are negative. That's my convention. All right, and then lastly, I'm going to note that according to my vector addition problem and my free body diagram, the x component of the tension in wire A opposes the tension in wire B, which is horizontal. If I want to solve for the tension in wire B, to get it out of side by itself, I'm going to find that it's the opposite of the tension in wire A, the x component. And the x component of the tension wire A is negative 98 newtons, so the tension wire B is also going to be 98 newtons. So now I have one of the tensions in the wires I was asked to find in this problem, 98 newtons in wire B. What about wire A? To solve for the tension in wire A, I need to recognize that I have a tool that I can use to solve for the hypotenuse of that 45-45-90 triangle. There's actually a couple of tools that you can use. You can recognize that a 45-45-90 triangle has a side ratio of 1 square root of 2, or you could simply use the Pythagorean theorem to solve, which is actually the same thing. So I'm going to use the Pythagorean theorem. The tension in wire A squared equals 98 squared plus 98 squared. And when I simplify this, I'm going to take the square root of both sides. I find that the tension wire A is 140 newtons. That's the other tension that I needed. So in problems where you have forces in 2 dimensions, you simply need to break those forces down into their one-dimensional components, account for them in their represented dimensions, and solve the problem just like we solved one-dimensional force problems.